Welcome back to the Sleepy Science Vault. You are here. That is the first thing. You have found your way to this quiet place. This voice in the dark, and whatever carried you through the hours between morning and now. Whatever the day asked of you, and whatever you gave it, that is finished. That chapter of the day has closed. What remains is this: the soft weight of the night, the dark behind your eyes, the particular permission of the late hours, which ask nothing and offer only rest. So let's begin with the rest itself. Feel your body, all of it at once, if you can. Not examining it, not evaluating it, just feeling its presence, the weight of it, the warmth of it, the way it is supported by whatever surface is beneath you. That support is complete. The surface holds every part of you with equal care. There is no part of you that is dangling, unsupported, unmet. You are held fully, without effort on your part. Let your shoulders soften now. Not dramatically, not with a performance of release, just a small permission, a quiet allowance that the muscles around your shoulders and your neck and the tops of your arms have been waiting for since some point this afternoon or this morning, when you first picked up the invisible weight of the day and began carrying it. That weight can be set down, right here. It doesn't have to go anywhere else tonight. It will still be findable in the morning if you need it. Let your jaw unclench. Let the tiny muscles around your eyes soften, the ones you don't usually notice until they release and you realize how long they had been holding. Let your hands uncurl, fingers loose, palms open. Let the long muscles of your back and your legs and your feet, which have been working all day, which have carried you everywhere the day required you to go. Let them recognize that the carrying is done. Notice your breathing slow, not because you are doing anything to it, not because you are practicing a technique, just because a body that is settling into rest breathes differently than a body in motion. And yours is already making that transition, already finding the slower, gentler rhythm that belongs to the night. You can simply notice it. The cool air arriving, the warm air leaving, the soft rise and fall that will continue faithfully and automatically through every hour of sleep. Allow the weight of the day to quietly. Allow the room to become quieter than it is. Allow yourself to become heavier in the good way, the settled, supported, completely released way with every breath. There is nowhere else you need to be tonight. There is nothing else that requires you. Tonight, we are going somewhere extraordinary. We are going somewhere so far from the ordinary scale of human experience that the very act of trying to imagine it is, in itself, a kind of release. Because the distances involved make every small anxiety, every unfinished thought, every tomorrow that feels too near, seem exactly what they are in the context of the cosmos. Very small things in a very large universe that will find their own resolution in their own time. We are going to space, to the deep places, the old places, the places where physics does things that language barely has words for, where matter becomes something that requires entirely new categories to describe, where time and space and gravity and light behave in ways that even the people who spend their lives studying them find beautiful and strange and not fully resolved. We are going to black holes, and we are going to the space between galaxies, and to the ancient light that has been traveling toward us since before the Earth existed, and to the places where stars are born, in slow clouds of gas and dust, that take millions of years to collapse, and to the places where stars die in explosions so large they briefly outshine entire galaxies. We are going to all of it, but slowly, gently, as a late-night journey through the most extraordinary landscape in the known universe, taken at the speed of a mind that is ready to drift. Come with me. Close your eyes. The universe is very large, and very old, and very quiet. Let's go in. There is a particular quality to the darkness between stars. It is not the darkness of a room with the curtains drawn. It is not even the darkness of a cave, or of deep water, or of any terrestrial environment. The darkness between stars is the darkness of genuine absence, the absence of matter, of photons, of anything at all, for distances that strain the imagination past its ordinary capacity. The distance from our Sun to the nearest star, Proxima Centauri, a small red dwarf star in the triple star system, Alpha Centauri, is approximately 4.24 light years. A light year is the distance light travels in 1 year, moving at its constant and extraordinary speed of approximately 300,000 kilometers per second. In 1 year, light covers nearly 10 trillion kilometers. In 4.24 years, it covers something like 40 trillion kilometers. If you tried to walk to Proxima Centauri at a comfortable walking pace, 4 kilometers per hour, 8 hours a day, it would take you approximately a trillion years. A trillion years. The universe itself is approximately 13.8 billion years old. The walk would take roughly 70 times longer than the universe has existed. Between us and the nearest star, essentially nothing. The space between stars is not filled with anything we can see or feel. It contains some hydrogen atoms, the interstellar medium, the diffuse gas that permeates the galaxy, but at densities so low that the best vacuum chambers ever created on Earth are vastly denser. The space between stars is emptier than anything human technology has ever produced. It is, for all practical purposes, vacuum, pure void, the absence of everything, and yet, even this void is not static. Even the emptiness is doing something. Quantum mechanics tells us that the vacuum is not truly empty, that at the smallest scales, pairs of virtual particles are constantly flickering in and out of existence, borrowing energy from the quantum uncertainty that permeates all of space, existing briefly and then annihilating each other, returning their borrowed energy, leaving no permanent trace. The vacuum hums in the language of quantum fields, with a kind of restless potential energy that we call the zero-point energy or the vacuum energy, an energy that cannot be removed or turned off. That is the irreducible minimum energy of empty space. Even nothing is doing something. Even the void between stars is, at the scale of quantum mechanics, alive with the most ephemeral possible kind of activity. But at the scale of the human senses, at the scale of the distances between stars, what the void offers is a quality of silence and stillness that has no parallel in ordinary experience. If you could somehow be placed in the middle of that void, in the space between the Sun and Proxima Centauri, equidistant from both, you would see 2 points of light, 2 stars, the Sun behind you, reduced to a very bright star, Proxima ahead, a dim red point, between them, nothing, no sound, because sound requires a medium to travel through, and there is no medium here, no sensation of temperature in the ordinary sense, because there is nothing to conduct heat or cold to your skin. Just the 2 distant lights, and the dark, the old old, dark. That image carries something in it that is, paradoxically, deeply restful. The vast emptiness of space is not threatening at this distance. It is simply present, simply what is. The dark between stars is not empty of meaning. It is the canvas on which everything else is painted. It is the context that makes the stars visible. Without the darkness, there would be no contrast, no distinction, no form. The darkness is not the absence of the universe. The darkness is part of the universe, perhaps the largest part. The light of stars is ancient. This is one of the most quietly beautiful things about looking at the night sky, and it deserves to be held for a very long time before moving on to anything else. When you look at a star, you are not seeing the star as it is now. You are seeing the star as it was when the light you are currently receiving left it, which could be years ago, or centuries ago, or millions of years ago, depending on the distance. The light has been traveling through the emptiness between stars for the entire duration of that time, and it arrives at your eye in the fraction of a second it takes you to look up, and it forms an image on your retina that represents a moment in the history of a star that may no longer even exist in the form you are seeing. The star you see might be gone. Some of the stars visible to the naked eye on a clear night are close enough that the light is only a few years old. The nearest ones, a handful of light years away, are showing us their state from the early years of this decade or the late years of the last. But many of the stars visible from Earth are hundreds or thousands of light years away. The light leaving them tonight will not arrive at our position for centuries or millennia. And the stars you can see with a good pair of binoculars or a small telescope, the stars of other galaxies, the stellar populations of the Andromeda galaxy, or the galaxies of the Virgo cluster. Their light has been traveling for millions or billions of years. The Andromeda galaxy, the nearest large galaxy to our own, is approximately 2.537 million light years away. The light that enters your eye when you look at it in the dark sky left Andromeda 2.537 million years ago. At that time, our ancestors were early Homo and Australopithecus, walking on the African savanna 2.5 million years before anything we would call civilization. That ancient light has been crossing the intergalactic void for all of human prehistory and history. It arrives at your eye tonight. There is something in that moment of arrival, in the connection it creates between your retina and a galaxy 2.5 million years in the past, that defies ordinary experience. You are receiving a message from before your species existed, a message written in photons, transmitted by the nuclear reactions of 100 billion stars, crossing a distance that dwarfs anything human time can hold, in arriving in your eye on this particular night, on this particular planet, in this particular moment of your life. The night sky is not just beautiful, it is a record. Every point of light in it is a different moment in the past, a different temporal snapshot of the universe, at different removes from us, all arriving simultaneously at the surface of the Earth and at the back of our eyes. When you look up, you are looking at a mosaic of different pasts, different depths of time, all visible at once. The star that is 100 light years away shows you the universe as it was 100 years ago. The star that is 1,000 light years away shows you 1,000 years ago. The faint smear of a distant galaxy shows you the universe as it was billions of years ago, when the Earth was forming or young, when the first complex organisms were only beginning to appear in the ancient seas. All of it visible at once, all of it arriving in a single night's observation. Let that settle in. Let it be as large as it wants to be. Your body is very still now. The room is quiet, and somewhere, many light years away in every direction, ancient light is traveling through the void. Some of it will arrive at Earth tonight. Some of it left its source before you were born. Some of it left before your grandparents were born. Some of it left before your species existed. It is all still coming. The universe doesn't stop sending. Let that be a kind of comfort in the dark. Black holes are the most extreme objects in the known universe, and yet they are also, in a strange and particular way, among the simplest. A black hole is a region of spacetime where gravity is so strong that nothing, no matter, no radiation, not even light itself, can escape once it has passed a certain boundary. That boundary is called the event horizon. It is not a physical surface, not a wall or a membrane. It is simply a threshold in the geometry of space, the point beyond which the escape velocity exceeds the speed of light. Escape velocity is the speed at which you would need to be moving to escape the gravitational pull of an object. From the Earth's surface, the escape velocity is approximately 11 kilometers per second. From the surface of the Sun, it is about 617 kilometers per second. As the mass of an object increases and its physical size decreases, as it becomes denser, the escape velocity at its surface increases. And if you could compress any given mass down to a small enough size, the escape velocity at that compressed surface would eventually reach and then exceed the speed of light. At that point, nothing can escape. Not a rocket, not a beam of light, not information of any kind. The boundary at which the escape velocity equals the speed of light is the event horizon. Inside it, the geometry of space-time is so distorted that what we normally call the future, the direction in time that everything in the universe naturally moves toward, points inward, points toward the center. There is no future direction that points outward. There is no trajectory that leads back out. This is not a prison with walls. It is a prison made of geometry itself, a place where the shape of space-time simply does not permit escape, where the concept of outward has ceased to be a valid spatial direction. And this makes the event horizon one of the strangest and most profound boundaries in the universe. Not a wall, not a substance, not something you could detect as you crossed it. If you were falling into a stellar mass black hole, you might not notice anything unusual at the moment of crossing the event horizon. The curvature of space-time there might be gentle enough that your body would feel nothing dramatic. You would simply cross a line in space, a line with no physical marker, no visible feature, no barrier to detect. And from that moment on, your future would lead only inward. You would have no way to signal back, no way to send information outward. The event horizon is the universe's perfect one-way door. What lies inside it? What happens to matter and information that fall past the horizon is one of the deepest unsolved problems in physics. We have equations that describe the geometry inside. We have theoretical predictions about the fate of infalling matter, but we cannot observe it directly because nothing that crosses the horizon can carry information back to us. The interior of a black hole is permanently, absolutely, unobservable from the outside. It is the ultimate hidden thing. There is something about the concept of the event horizon that speaks to a very deep part of human experience. The idea of a threshold you cannot return from, a line that is invisible until you've crossed it, and which, once crossed, changes everything. In physics, this is the event horizon of a black hole. In life, these moments exist too, though they are softer, less absolute, more reversible in most cases. Moments of commitment, moments of no return, moments when you have crossed from one state of being into another, and the world on the other side is fundamentally different from the world on this side. But what the black hole's event horizon offers, in its stark mathematical elegance, is the pure form of this idea, the irreducible essence of a threshold. And there is something clarifying about that, something that makes the concept available for contemplation in a way that the messier, less definite thresholds of ordinary life don't always permit. The event horizon says, here is a boundary. It is not arbitrary. It is not socially constructed. It is woven into the geometry of space-time itself. It is the place where the escape velocity equals the speed of light and where no exceptions are possible. And on this side of it, the universe continues in all its ordinary complexity. And on the other side, unknown, not threatening, just unknown. The interior of a black hole is one of the most thoroughly unknown things in science. We have theories about it, good theories, mathematically consistent theories, theories that make specific predictions about what an infalling observer would experience. But those theories cannot be tested. The information cannot come back. And so we hold the interior of a black hole as the most perfect example of permanent scientific unknowing that exists. There are things we will never know, not because we lack the cleverness or the instruments, but because the universe has placed them irretrievably behind a geometric boundary that makes knowing them impossible in principle. And that is all right. There can be rest in the existence of permanent mystery, in the acknowledgement that not everything needs to be known, that some things can remain hidden without threatening us, that the universe can contain regions of absolute unknowing, and the universe is still the universe, and we are still here, and everything continues. The black hole at the center of our galaxy has a name, Sagittarius A star, pronounced Sagittarius A star. It sits approximately 26,000 light years from Earth, at the center of the Milky Way, hidden behind dense clouds of gas and dust that make it invisible in ordinary optical light. You cannot see it from a dark sky site, even with a large telescope. By looking for it directly, it hides behind the material of the galaxy's crowded inner regions, obscured by everything between us and it. But it is there. Its presence has been known for decades, inferred from the behavior of stars near the galactic center. Those stars, a cluster of young, hot, massive stars orbiting in the densely packed region within a few light years of the galactic center, move in ways that betray the presence of an enormous invisible mass. They orbit it the way planets orbit the sun, but far faster, in periods of years rather than centuries, tracing orbits around a point in space where nothing optical is visible. The motions of these stars have been tracked by astronomers over decades, building a precise picture of the gravitational mass at the center of the galaxy. The mass they imply is approximately 4 million times the mass of our Sun, compressed, apparently, into a region smaller than the distance from the Sun to the inner planets of the solar system. This is a supermassive black hole. All large galaxies appear to have supermassive black holes at their centers, objects with masses ranging from millions to billions of solar masses, formed in processes that are still not fully understood, possibly growing from smaller black holes that merged and accreted mass over billions of years. The supermassive black hole and the galaxy appear to grow together in a relationship so intimate that the mass of the central black hole is tightly correlated with the properties of the galaxy's central bulge, a correlation that suggests they shaped each other, regulated each other, grew in response to each other across cosmic time. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star itself. It was a blurry orange ring, the light from hot gas orbiting the black hole at close range, bent by the extreme gravity into a circular pattern with the dark silhouette of the event horizon at its center. Not sharp, not detailed in the way of ordinary photographs, but real, a true image of the shadow of the event horizon, of the black hole at the center of our galaxy, a circle of dark, 26,000 light years away, surrounded by a ring of impossibly hot, glowing, orbiting gas. The first direct observation of the thing at our galaxy's center, the thing around which our entire galaxy, all 200 to 400 billion stars of it, slowly orbits. We orbit a black hole, not closely, not in any way that affects our daily lives or the physics of our solar system. At 26,000 light years, the influence of Sagittarius A star on our orbit around the galactic center is simply part of the background gravity of the galaxy, indistinguishable from the combined pull of all the other matter. But technically, gravitationally, in the bookkeeping of the galaxy's dynamics, we are in orbit around a 4 million solar mass black hole. The Sun takes approximately 225 to 250 million years to complete one orbit of the galactic center. This is called the galactic year, or the cosmic year. The last time the solar system was in this position relative to the galactic center, completing the circuit and arriving back here, the Triassic period had just begun on Earth. The first dinosaurs were only newly arrived. The continents were still partially merged into Pangaea. We have traveled one complete circuit around the galaxy's black hole since the dinosaurs first appeared. Let that image drift through you softly. The slow, enormous orbit. The galaxy's center, hidden behind its veils of dust. Always there. The solar system, patient and precise, following its ancient gravitational path through 200 million years of change on the small, warm planet that rides within it. Time behaves differently near a black hole. This is not metaphor, not a way of speaking loosely about the feeling of enormity or the weight of cosmic scale. It is a precise, measured, experimentally confirmed prediction of general relativity, the theory of gravity published by Albert Einstein in 1915. In general relativity, gravity is not a force in the Newtonian sense, not an invisible pull acting at a distance between massive objects. Gravity is the curvature of spacetime, caused by mass and energy. Massive objects curve the spacetime around them, and other objects move through that curved spacetime along the paths that the curvature defines. What we experience as the pull of gravity is actually the geometry of the universe bending trajectories inward. And one of the consequences of this space-time curvature is gravitational time dilation. Time passes more slowly in a stronger gravitational field. This is not a theoretical abstraction. It is measurable. The clocks on GPS satellites orbiting Earth at altitude, where gravity is slightly weaker than at the surface, run slightly faster than clocks on the ground. The satellite navigation system has to account for this difference. If it didn't, GPS accuracy would drift by kilometers per day. The time dilation predicted by general relativity is built into the software of every GPS receiver in the world. Near a massive object, like a black hole, where gravity is extreme, the effect becomes extreme. A clock close to the event horizon of a black hole would tick extraordinarily slowly compared to a clock far away. An observer watching from a safe distance would see the infalling clock and any infalling person or object slow down asymptotically as it approached the horizon. From the outside, the infalling object never quite reaches the horizon. It slows and slows, redder and dimmer, as the light it emits is stretched by the gravitational field, until it fades from view entirely. It appears to freeze at the horizon. From the perspective of the infalling observer, though, nothing unusual happens at the horizon itself. They cross it in finite time by their own clock. They fall through. The universe outside, visible through the stretching geometry ahead of them, has run forward enormously, because from their perspective, they have been falling through a region of extreme time dilation, and the outside universe has aged enormously during their brief, subjective experience of crossing. The two perspectives are both correct. Both are physically valid descriptions of the same event from different reference frames. There is no single universal and now. That is one of the deepest things relativity tells us, and it is worth sitting with. There is no moment in the universe that is simultaneously now for all observers. The now of a person near the horizon of a black hole is a completely different slice of space-time than the now of a person far away, watching. They don't disagree about facts. They both correctly describe the physics from their own frames, but they are, in a meaningful sense, experiencing different aspects of the same reality. Time is not a river that everyone swims at the same speed. Time is a fabric, curved by mass, stretched by motion, experienced at different rates in different gravitational environments. The difference between your experience of time and the experience of an imaginary person on the surface of a neutron star would be enormous. Time for them would pass slower by an extraordinary factor compared to you, sitting here in the weak gravity of Earth's surface. You experience time differently than someone higher in altitude, standing on a mountain. The difference is tiny, nanoseconds over a lifetime, unmeasurable by any human sense. But it is there. General relativity predicts it. Precise clocks confirm it. Time is already curved around you, though you don't feel it. Soften a little more. Let the thought of curved time settle around you like something you can rest in, not a disorienting thought. The curvature of time near you, in Earth's gentle gravity, is too small to feel, but the knowledge of it is a kind of spaciousness, a reminder that the universe is larger and stranger and more interesting than it appears from the surface of ordinary experience. You are floating in curved space-time right now. You have always been floating in it. It holds you with the same faithfulness as the surface beneath you. Stars are born in silence, or not silence exactly. In the language of sound, there is no sound in space, no medium through which sound waves can travel between the stars. But in the language of sensation and scale, there is a quality to the birth of a star that is the opposite of explosive. It is gradual, it is patient, it takes millions of years. A star begins as a cloud, a nebula, an enormous volume of gas and dust, mostly hydrogen, drifting in the space between existing stars. These clouds can be light years across, vast, tenuous, cold. The temperature in the densest parts of a molecular cloud is around minus 260 degrees Celsius, just a few degrees above absolute zero. The gas is so diffuse that it would qualify as an extraordinarily good vacuum by the standards of any laboratory on Earth. But the cloud is not uniform. There are denser regions and thinner regions, places where slightly more gas has accumulated, creating slightly stronger gravity, pulling slightly more gas inward. The process is slow. The timescales of gravitational collapse in an interstellar cloud are measured in millions of years. But the direction is one way. The denser regions grow denser. The gravity grows stronger. The gas falls inward, slowly, patient, accumulating. As the cloud collapses, it fragments. Different regions within it reach their own collapse thresholds independently, and each one begins forming its own concentration, its own protostar. The cloud that begins as a single entity becomes, over time, a stellar nursery, a region where dozens or hundreds or thousands of stars are being born simultaneously out of the same parent cloud, each one condensing from its own fragment of the original gas. As a fragment collapses, it heats. The conversion of gravitational potential energy into thermal energy warms the gas at the center of the collapse. The protostar, a ball of hot, dense gas, still gathering material, still accreting from the disk of gas and dust that swirls around it, grows hotter, denser, and then, after millions of years of collapse, something happens. The temperature at the center of the protostar reaches the threshold at which hydrogen nuclei, protons, can overcome their electromagnetic repulsion and fuse together. Nuclear fusion ignites. A new star turns on. The energy released by fusion creates an outward pressure, a radiation pressure, a thermal pressure that balances the inward pull of gravity. The star finds an equilibrium, a stable state in which the tendency to collapse is exactly balanced by the tendency to expand. In this equilibrium, the star will spend most of its life fusing hydrogen, radiating energy, maintaining its balance between gravity and pressure. This moment, the ignition of fusion, the balance point between collapse and explosion, is the moment a star is born. It happens in the dark interior of a collapsing cloud, invisible, surrounded by gas and dust. The newborn star radiates, but for a time, that radiation cannot escape the surrounding material. The nursery hides its children. Eventually, the stellar winds and the radiation pressure from the new stars blow away the surrounding gas and dust. The nebula is dispersed. The stars are revealed, young, hot, bright, clustered together in the open cluster that formed from their shared parent cloud. They drift apart over millions of years, scattered by the gentle gravitational interactions of their journeys through the galaxy. The sun was born this way, in a nebula, perhaps in a cluster 4.6 billion years ago. The sibling stars that formed with it in the same parent cloud are now scattered across thousands of light years. We don't know which stars were born alongside the sun. We can't identify them with certainty. The original siblings have dispersed beyond recognition, and each one is now just another star in the galaxy, navigating its own orbit, carrying within it the same original chemistry as our sun, but otherwise unrecognizable as family. The birth of the sun, 4.6 billion years ago, was not a dramatic event from the perspective of the galaxy. It was one of many, one of perhaps 100 billion stars born in the Milky Way over its history. One proto-stellar cloud fragment, collapsing over millions of years, igniting, finding equilibrium, and beginning the long, stable life it still lives today. The sun is about halfway through its hydrogen-fusing lifespan. It has been burning for 4.6 billion years, and it has approximately another 4.5 to 5 billion years of hydrogen fusion remaining. Then the hydrogen in its core will run out, and the sun will change, expand into a red giant, shedding its outer layers, eventually settling into a white dwarf, cooling over billions of years into a cold, dark remnant. 5 billion years from now. That is a time too large for anxiety. 5 billion years from now, whatever exists on this planet, or in this solar system, or in this part of the galaxy, will be unrecognizably different from today. The sun's eventual death is not something to carry. It is something to set down, lightly, in the enormous distance of future time, where it belongs. When a massive star dies, it dies dramatically, but not the way dramatic is usually meant, not quickly, not in a moment. A star that is 8 or more times the mass of the sun spends millions of years, sometimes tens of millions, fusing hydrogen and then helium, and then heavier elements in the layers of its core, building up an onion-like structure of progressively heavier elements, hydrogen in the outermost shell, helium below, carbon, neon, oxygen, silicon, and at the center, eventually, iron. Iron is the end of stellar nucleosynthesis. Every element that can be fused in a star releases energy in the process. The product of the fusion is lighter than the parts that went into it, and the mass difference becomes energy according to Einstein's most famous equation. But iron is different. Fusing iron absorbs energy rather than releasing it. Iron is the most stable atomic nucleus. It sits at the bottom of the binding energy curve, the place where no more energy can be extracted from fusion or fission. When iron accumulates in the core of a massive star, the energy source that has been holding the star up against its own gravity disappears. The iron core collapses in less than a second, in a fraction of a second actually, in approximately a quarter of a second. The iron core of a massive star collapses from the size of Earth to the size of a city, a sphere roughly 15 kilometers in diameter. The density of atomic nuclei, the density of matter so extreme that the protons and electrons in the atoms are forced together into neutrons, releasing an enormous flood of neutrinos. In the process, neutrinos are nearly massless, nearly undetectable particles that interact with ordinary matter only through the weak nuclear force and gravity, so weakly that a neutrino can pass through a light year of lead with only even odds of interacting with anything. They are, ordinarily, the most antisocial particles in the universe, but in the collapse of a stellar core, the density becomes so extreme that even neutrinos are briefly trapped. The core becomes opaque to its own neutrinos. The pressure builds, and then, In one of the most violent events in the universe, the core bounces, stiffens against further compression as the neutron matter resists, and a shock wave propagates outward through the star's remaining material. The outer layers of the star are blown off in an explosion that, at its peak, outshines the entire galaxy containing it. For a brief period, days to weeks, a single star produces as much light as all the hundreds of billions of stars of its galaxy combined. This is a supernova, the material expelled in the explosion, the gas and dust that was the star's outer layers, enriched with the heavy elements the star spent its life synthesizing, expands outward into the surrounding space. Over thousands of years, it forms a supernova remnant, an expanding shell of hot, glowing gas, beautiful in the images that modern telescopes produce. The Crab Nebula, Cassiopeia A, the Veil Nebula, each one the remains of a star that ended its life in this way, and the heavy elements in that expanding gas, the carbon, the oxygen, the nitrogen, the silicon, the iron, mix with the surrounding interstellar medium. They become part of the next generation of molecular clouds. They are eventually incorporated into new stars, into the gas disks around those stars, into the planets that form from those disks, into us. The carbon in your body was forged in the nuclear reactions of stars, the calcium in your bones, the iron in your blood. Every atom heavier than hydrogen and helium in your body has a stellar origin, was synthesized in the nuclear furnace of a star that lived and died before the sun was born. The heaviest elements, gold, platinum, uranium, were formed in the most extreme events, the mergers of neutron stars, the most energetic collisions in the universe, producing in a fraction of a second more mass in heavy elements than the sun will ever synthesize. You are made of stardust. This is not a metaphor, it is chemistry. The atoms in your body have a history that goes back billions of years, through generations of stellar birth and death, through supernovae and neutron star mergers, through the slow swirl of molecular clouds, and the patient collapse of protostellar fragments. You are the universe, looking at itself, assembled from the nuclear byproducts of stars long dead, organized by chemistry and biology, into something complex enough to be curious about where it came from. The universe is approximately 13.8 billion years old. It began, if began is the right word, for something that may have had no predecessor, for which the concept of before may not apply, in a state of extraordinary density and temperature, and has been expanding ever since. The expansion of the universe is one of those concepts that is easy to misunderstand, and the misunderstanding leads to an image of the universe that is subtly wrong in an important way. The universe is not expanding into anything. There is no pre-existing space for it to expand into. What is happening is not that matter is moving outward through a pre-existing void, but that space itself is expanding. The metric of distance between objects that are not gravitationally bound to each other is increasing. The fabric of space is stretching. The analogy that is most often used is raisins in a rising bread. As the bread rises, the raisins, which are not moving through the bread, but are embedded in it, move apart from each other. Every raisin moves away from every other raisin, not because any of them are traveling, but because the medium between them is expanding. The further apart two raisins are to begin with, the faster they appear to move apart, because more expanding medium lies between them. In the universe, the far-away galaxies are receding from us, not because they are moving through space, but because the space between us is increasing, and the rate of recession increases with distance. The most distant galaxies we can observe are receding at speeds that, in the conventional sense, exceed the speed of light. Not because any object can move faster than light through space, but because enough space can expand fast enough to carry objects apart faster than light. This means there is a boundary to the observable universe, a distance beyond which the expansion of space is so rapid that no light from objects beyond that distance has been able to reach us in the 13.8 billion years since the universe began. The observable universe, the sphere of space from which light has had time to reach us, has a radius of approximately 46 billion light years. Beyond that boundary, space continues. Matter and galaxies and stars, and perhaps other observers continue, but we cannot see them. Their light has not had time to arrive. We live in a cosmic horizon, a sphere of observation beyond which the universe simply does not communicate with us. The universe may be infinite. The observable universe is finite. We are inside a sphere of knowing, surrounded by an unbounded unknown. And the unknown is not threatening. It is simply the rest of the universe, doing whatever it does, unaware of us, as we are unaware of it. An unimaginable volume of space, full of galaxies and stars, and perhaps other life, none of which has any awareness of this particular planet, this particular evening, this particular person lying in the dark, listening to a voice talk about the cosmos. You are the only universe observer at this exact location in spacetime. No one else is seeing the cosmos from precisely here, precisely now. That is a kind of uniqueness so rare and so absolute that it almost functions as a gift. Dark matter and dark energy are two of the most important and least understood ingredients of the universe. Dark matter is whatever it is that accounts for approximately 27% of the total mass energy content of the universe. It does not emit, absorb, or scatter light at any wavelength we can detect. It is called dark because it is invisible to every instrument we have built to detect electromagnetic radiation. We know it exists because of its gravitational effects on the rotation of galaxies, on the way galaxy clusters bend light, on the large-scale structure of the universe. Something gravitating is there. We don't know what it is. Every candidate particle that physicists have proposed for dark matter, WIMPs, axions, sterile neutrinos, primordial black holes, has either been ruled out by experiments or remains undetected. Decades of increasingly sensitive experiments designed to directly detect dark matter particles have found nothing. This is one of the most active and frustrating areas in physics. Something comprises more than a quarter of the universe's content. Something that determines how galaxies form and how clusters of galaxies are structured. Something without which the universe, as we know it, would not exist. And we have no idea what it is. Dark energy is even more mysterious. It is whatever accounts for the accelerating expansion of the universe. In 1998, two independent groups of astronomers studying distant supernovae, using the known luminosity of certain types of supernovae as standard candles to measure distance and recession velocity, found that the expansion of the universe is not slowing down, as gravity would suggest it should, but speeding up distant galaxies are receding faster than expected. Something is pushing space apart, driving the expansion to accelerate. That something is called dark energy. It appears to account for approximately 68% of the total mass energy content of the universe. If you add up dark matter and dark energy, you get approximately 95% of the universe's total content. The ordinary matter, the atoms, the stars, the planets, the gas clouds, the galaxies, everything that can be seen or touched or measured with instruments, comprises only about 5% of the universe. We understand 5% of the universe. The other 95% is, in the most literal scientific sense, completely unknown. That statement has the potential to be disturbing if you approach it from the wrong direction, from the right direction, from the direction of curiosity and wonder rather than anxiety. It is one of the most extraordinary things in all of science. The universe is vast and old and almost entirely unknown to us. We are at the very beginning of understanding it. Every tool we have, every satellite and telescope and particle detector and gravitational wave observatory is revealing more and more of the 5%, while the 95% maintains its patient, dark silence. The universe contains far more than we know. That means there is far more to discover. That means the work is not finished. That means the most interesting chapters of human understanding of the cosmos have not yet been written. There are gravitational waves. Einstein predicted them in 1916. As a consequence of general relativity, he predicted that when massive objects accelerate, they produce ripples in the fabric of spacetime that propagate outward at the speed of light. Gravitational waves, stretches and compressions in the geometry of space itself, traveling through the universe like ripples on the surface of a pond. He thought they would be too small to detect. He was almost right. The gravitational waves produced by the most common accelerating masses, planets orbiting stars, binary stars orbiting each other, are extraordinarily small. By the time they reach Earth from astronomical distances, they stretch and compress the geometry of space by amounts that are almost incomprehensibly tiny. The first directly detected gravitational wave on September 14, 2015, stretched and compressed a detector 4 kilometers long by less than 1,000th the diameter of a proton. This is approximately 1/10,000th the size of a hydrogen atom. The instruments that detected it, the LIGO detectors in Louisiana and Washington state, are among the most sensitive measuring devices ever built. They detect this infinitesimal stretching and compressing of space by splitting a laser beam, sending the two halves down 2 perpendicular 4-kilometer tubes, bouncing them off mirrors, and recombining them. If the two paths are exactly equal length, the light waves cancel each other out in a specific pattern. If one path is even slightly longer or shorter than the other, by the passage of a gravitational wave, the cancellation changes in a detectable way. The first gravitational wave event detected, GW150914, named for the date of its detection, was produced by 2 black holes merging. 2 black holes, one of approximately 36 solar masses and one of approximately 29 solar masses, spiraling toward each other over a period of millions of years, accelerating as they lost energy to gravitational radiation, and finally merging in a fraction of a second into a single black hole of approximately 62 solar masses. The three missing solar masses, the mass of three suns, were converted entirely into gravitational waves in that fraction of a second. The peak power output of the merger, in the last moments before they combined, was greater than the combined luminosity of all the visible light from all the stars in the observable universe. All of it in the form of gravitational waves, silent, invisible, passing through everything and after, traveling approximately 1.3 billion years across the universe. Those waves, diminished to their extraordinary tininess by the distance, passed through the Earth on September 14, 2015, stretched and compressed the LIGO detectors, and were detected. The signal lasted about a fifth of a second of data, containing the record of two black holes, each containing the compressed remnants of massive stars, each invisible, each separated from us by 1.3 billion light years, spiraling together and merging. We heard it. We built an instrument sensitive enough to hear the space-time ripples of merging black holes a billion light years away. And we heard it. That fact deserves a moment of quiet astonishment, of the kind that is not excitement or agitation, but something more like wonder that settles rather than stirs. The human capacity to build instruments of extraordinary sensitivity and to connect them to mathematical theories that were correct, that described reality accurately, and to use that combination to detect something that Einstein thought would never be detected. That is one of the more remarkable things our species has managed. We heard the universe. Let your body be very still. The gravitational waves are passing through you right now. Not from that specific event. That signal has long since dispersed. But gravitational waves from other events, other merging black holes, other colliding neutron stars, perhaps other sources not yet characterized, are passing through the Earth and through you at this very moment, stretching and compressing the geometry of your body by amounts so small that nothing could ever measure them. Not even LIGO. The universe is vibrating through you, gently, continuously, in the silent language of space-time. Something is always passing through. The cosmic microwave background is the oldest light in the universe. It was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into stable hydrogen atoms for the first time. Before this event, the universe was a hot, opaque plasma. Matter and radiation so thoroughly mixed that light could not travel freely, bouncing instead off free electrons in a continuous fog. The universe was opaque to its own light. When the electrons and protons combined into atoms, the fog lifted. The universe became transparent. Light could travel freely for the first time. And that light, the first light to travel freely through the universe, has been traveling ever since, in every direction. For 13.4 billion years, it has been stretched by the expansion of the universe from the short wavelength, high-energy light it was when it first traveled freely into microwaves, very low-energy radiation. It fills all of space, uniformly, in every direction. A faint glow of microwaves arriving from every direction in the sky at once. The same temperature in every direction, approximately 2.7 degrees Kelvin, with tiny variations of less than 1 part in 100,000. Those tiny variations encode the structure of the early universe. The slightly denser, and slightly less dense regions in the 380,000-year-old universe that eventually, through gravitational collapse over billions of years, became the galaxies and galaxy clusters we see today. The pattern of variations in the cosmic microwave background is a map of the seeds of structure in the universe, the quantum fluctuations of the earliest moments written into the temperature of ancient light, preserved across 13.4 billion years. We can read it. We have mapped it in extraordinary detail. We have extracted from it the age of the universe, the proportions of matter and dark energy, the geometry of space. The cosmic microwave background is the most perfect dataset in cosmology, the universe's own record of its earliest accessible state. It is arriving at you right now. The microwave background pervades all of space. Every cubic centimeter of the universe contains this ancient radiation. Every square centimeter of your skin is being touched gently and continuously by photons that are 13.4 billion years old. Photons that have been traveling since before Earth existed, since before the Milky Way was fully formed, since before the first stars lit up the darkness of the early universe. The oldest light in the universe is touching you right now, gently, from every direction, without pause. The universe will end, but not soon. The current best understanding of the far future of the universe, given what we know about dark energy and the physical processes available to us, traces a timeline that makes the current age of the universe seem like a heartbeat at the beginning of a very long story. In approximately 5 billion years, the sun will exhaust its hydrogen fuel and expand into a red giant, engulfing the inner planets. Earth, if it still exists, will be consumed or at minimum sterilized, but the universe will continue. In approximately 1 to 500 billion years, the last new stars will stop forming as galaxies exhaust their supplies of cold gas. The stellar population of the universe will gradually age and die out. Massive blue stars first, over millions of years, sun-like stars over billions, small red dwarfs over trillions. In approximately 10 to the power of 14 years, 100 trillion years, the last red dwarf stars will finally exhaust their hydrogen and fade. The universe will consist primarily of stellar remnants, white dwarfs, neutron stars, black holes, and cold, dark planetary bodies drifting through the dark. After that, on timescales so large that the names of the numbers become almost meaningless, the remaining matter in the universe will slowly evaporate through processes like proton decay, quantum tunneling, and the thermal evaporation of black holes. Through the process Stephen Hawking theorized, Hawking radiation, black holes themselves will evaporate. Through the quantum process that Hawking described, black holes slowly lose mass by emitting radiation, a consequence of quantum mechanical effects near the event horizon. A stellar mass black hole will take approximately 10 to the 67th power years to evaporate. A supermassive black hole like Sagittarius A star will take approximately 10 to the 100th power years. A googol of years. A googol of years from now, the last black holes will have evaporated. The universe will consist of nothing but a cold, diffuse gas of elementary particles, photons, neutrinos, electrons, and positrons, drifting in an ever-expanding space, cooling asymptotically toward absolute zero. The universe will, if current physics is correct, end in cold and dark and silence. But here is the thing about this far future darkness. It is so far away in time that it functions not as a source of dread, but as a kind of permission. A googol of years is 10 to the 100th power years. Written out, it is a 1 followed by 100 zeros. The current age of the universe is a 1 followed by 10 zeros. The universe will run for roughly a googol divided by 10 billion, more times its current age, before the last black holes fade. Whatever you are worried about tonight does not need to last a googol of years. Whatever feels urgent or unresolved or close, it will find its resolution long, long, long before the last photons cool. There is time. There is more time than you can imagine. The night has become very deep. The thoughts are quieter now, slower, less sharp at their edges. The universe continues its long work in the silence of the space around you. Photons from distant stars traveling through the void. Gravitational waves stretching the fabric of space by imperceptible amounts. The cosmic microwave background touching your skin with its 13.4 billion-year-old light. The supermassive black hole at the center of the galaxy waiting in its patient darkness, 26,000 light years away, invisible behind its veils of dust. All of it continuing, all of it doing exactly what it does, regardless of whether anyone is watching, regardless of the hour, regardless of whether any mind in the universe is conscious of it in this particular moment. The universe is perfectly capable of going on without us, and tonight it will. It will go on through every hour of your sleep, expanding and cooling and burning, emerging and emitting its ancient light in every direction, from every star. All of it at once, all of it, always. You don't have to hold any of it. You never did. Let the universe be the universe. Let the black holes hold their darkness and their silence and their patient existence far beyond the reach of anything you need to think about tonight. Let the ancient light do its traveling. Let the stars do their burning and their dying and their exploding and their slow collapse into new generations of worlds. Let the galaxy turn slowly around its hidden center. Let time do what time does. Curve gently, flow forward, stretch and slow in the gravity of massive things, and accelerate in the openness of space. Always forward, always carrying everything into whatever comes next. And let yourself be here, just here, in this room, in this body, in this warmth. Your breath is very slow now, very gentle. The thoughts are barely thoughts anymore. They are more like impressions, colors, the faint echo of images that arrive and dissolve without requiring anything. The universe is 13.8 billion years old, and it will last for a googol more years. And you are in the middle of it, right now, this tiny, warm, improbable thing made of stellar ash, resting on a planet orbiting a middle-aged star in the outer arm of a galaxy that is one of 2 trillion galaxies in the observable universe. You are here. You are the universe, briefly, quietly, exactly yourself, and you are resting as the stars rest between their burning, as the space between galaxies rests in its ancient cold, as the black holes rest in their enormous patience, as the cosmic microwave background rests in its endless, gentle, cooling drift through all of space. Everything rests, everything drifts. Let the cosmos carry you now. You are already part of it. You have always been part of it. Drift with it, slowly. The dark is warm. The universe is vast, and you are very, very small, and very, very held. And the night is long and full of stars, and the stars are made of the same things you are made of. And everything is connected through 13.8 billion years of cosmic history. And all of that is very beautiful and very far away and very quiet. Rest, sleep well, and good night.